Okay, I think we are screen sharing. Awesome. Okay, so I like to do my memes and GIFs, so we're gonna get those out of the way. If you're in my 315 class, as in Kin 315, they're the same meme, so I'm sorry. Um, but my 6-year-old brother's teacher asked the class what their favorite season, or what's their favorite season, and he said garlic powder. I would agree with that. I think garlic powder is at that or Lowry's garlic salt. It's really, really good. Um, Also this.
You ever put like garlic powder or garlic salt in eggs?
Yes,
Super good.
fantastic. But also, yeah, why did they make the close ad button so small? I don't even know. And then this is the last one. Free hugs or not. Yeah. Anyways, that's what I got. So to business. This week we are talking about chapter 3 and 4 in the textbook, which is on percentiles and measures of central tendency. So, a lot of the measures we'll talk about in this area, you guys have probably worked with before. Some of you may have also worked with percentiles, but we're going to do it in the context of using frequency distribution tables. So, we're building on some of the foundational steps and stuff that you guys used last week in your activity. But we'll start with percentiles first. So, percentiles, the definition the book gives is it's a point or position on a continuous scale of 100 theoretical divisions. Okay, so we have to say theoretical because not every single type of measurement is going to be on a scale from 0 to 100, right? So percentiles or using percentiles is kind of a way of normalizing data such that we can make a bunch of different measurements equivalent on the same scale, right? So something that does that is called a standard score. Okay, and we'll go over quite a few standard scores throughout uh, mostly the first 3 weeks of the semester. So percentiles is our first type of standard score. But like I said, that allows us to compare a lot of different things to each other. Okay. So if we have people from different populations, we could say people from population A are seemingly very different from people in population B. But if we put them all on the same percentile score or percentile scale, then we can actually evaluate if or how similar they are to each other. And then we can also, these are helpful when we're looking at different units of measurement. So if I wanted to say, like, what is health status, or I'm assessing people's health status using a lot of different variables. I could measure that by using their heart rate or resting heart rate. I could do it by looking at their blood pressure. I could look at it, with their VO2 max. And basically, what the percentiles do is we put them per each measurement on its own scale of 0 to 100. And then we can say, okay, well, based on these percentiles, people who had their heart rate measured are semi-similar to other people who had their VO2 max measured. So it's a good way of comparing apples to oranges. And also this kid, what cookie, right? But we can compare seemingly different things to each other when we standardize them. Okay, so let's look at an example of what this would mean or how it would translate, right? So we say Bob can do 40 push-ups, right? Is this good or bad, right? You need some type of comparison, okay? So to do this, we need some context about who Bob is, right? And usually within research, we get this information from the sample that we're working with, right? So let's say that Bob is a bodybuilder. Ha, ha, you get it? Anyways, so maybe 40 push-ups for a bodybuilder is like really bad, right? Because they're supposed to be super strong and have good, well, some of them might not have good muscular endurance, but you would hope. that they train not to just get bulky, but functional anyways. That's a whole other class. But, maybe 40 push-ups for a bodybuilder isn't that much, right? So in terms of this type of sample or this target of a sample, maybe 40 push-ups is in the 30th percentile, okay? But maybe Bob is a middle-aged man and 40 push-ups is like, damn, son, that's good, right? And then maybe 40 push-ups is in the 94th percentile, right? So when we have, this is a good example, we have two different samples or two different populations that we're pulling from, we can compare them to each other and say, well, on this scale, right, for this type of person, we would evaluate them in this way. So just saying, right, or giving data doesn't always, it's not always the best method. We might need something like percentiles to evaluate different groups. Okay. So in terms of the bell curve, which we'll get into next week, I'm pretty sure it's next week. Anyways, the bell curve, right, normal distribution, will become a very, very common word in this class. And it might look familiar to some of you if you've taken an undergraduate statistics class before. But basically, just to give a rundown of what percentiles mean in terms of the distribution, generally when you collect a sample, you want it to be normally distributed or have a bell-shaped type of curve. And what this indicates is the frequencies, right, of who we are collecting. So if we've got, let's say 100 people, right, we would expect the mean of those 100 people to be right smack in the middle. And we'll come back to this when we talk about our measures of central tendency. As in a perfect normal distribution, all of our measures of central tendency will be in the middle, okay? And then from this mean, usually there's a good chunk of people who are kind of surrounding that mean, right? Or we have higher frequencies of people for whatever unit we're measuring closer to the mean. And then as we get further and further away from the mean, which we talk about in terms of standard deviations, right, we get smaller and smaller and smaller frequencies. So in terms of the percentile and how we read it alongside the normal distribution, we say the 0th percentile is down on this end, where we have kind of below the mean end or negative standard deviations, and then the 100th percentile is up at the top, okay? So the percentile row is right here. So you can see it's not perfectly like 0 is all the way at the end, right? Typically within a perfectly normal distribution, most of the time 50% will be on this side, 50% of your sample will be on this side, okay? And then 75%, so if you want to look at, like who is in the top quarter, that's just under one standard deviation from the mean. Same thing with the 25%, okay? So there's a question on your activity this week, if I'm remembering correctly, that asks you, like, what percentile would you expect these people to be in based on if they're, low performance, intermediate performance, or advanced performance type people based on the variable that's collected. And so you can kind of use this guesstimation. Where's my pointer? You can use this guesstimation here to kind of figure out that question. So that's a hint for later. Do I have any questions from the people so far?
Yeah, what's the normal curve equivalence at the very bottom?
The normal curve, well, we don't go over that stuff in this class. So,
for sure.
TBH, I don't really know. What we do go over is percentiles, we do standard deviations, and then we also go over the empirical rule, which is what these percentages are in here. But yeah, I don't know. Okay, so let's go into calculating percentiles. I think this part, the actual calculations themselves aren't very difficult, but a lot of times it's the wording that gets to people. So I would say in your quizzes and when we get to the exams or your activities, just make sure you're being careful with your wording. Because percentiles are going to be uh, kind of determinant on the unit of measurement that you're using. So a lot of times people will say, oh, someone was at or less than a given raw score. And we can't always say less than, right? So 100th percentile is kind of considered like this is the best score you could get based on the measurement or unit of measurement that we're collecting. And the 0th percentile is kind of considered the worst end. So I like to use the wording that the percentile represents the percentage of values that fall at or worse than a given point. So in terms of the distribution, since 0 is at one end and 100 is at the other end, we just say worse than is kind of similar to less than or equal to, but there are examples that we'll have in the class. I do know specifically in the activity where the worse than score is actually kind of like the larger quantity based on the numbers that you're looking at. So speed is a good example, right? Someone who is running a race and they have a big time, like they ran a mile in 10 minutes, right? That would be considered kind of a low score versus someone who ran a mile in 4.5 minutes, right? Which would be considered closer to the 100th percentile. So time is a good example where it's not always a less than explanation. Yeah.
Would you consider like these percentiles as like ordinal data?
In a way, I suppose they could be.
Okay.
But when you're classifying data, it largely represents what's been collected. So I guess if you were saying like maybe you collected data with a certain unit of measurement and then you converted it into a percentile and you wanted to see if people's percentiles from different populations were different from each other, then you could use that, in which case I would say it's ordinal because you're ranking people, but you're not necessarily saying like what the unit discrimination is between, say, the 25th percentile and the 50th percentile. Or you could even close the gap more and you don't really know what the unit discrimination would be between the 50th and the 51st. So, yes, to answer. Long-winded question, but yes. But if we use the 85th percentile, so if I give you wording, right, that says like, oh, someone's at the 85th percentile, at being our keyword here, right, you would say that their raw score, right, is equal to or better than, right, the other raw scores within the distribution, okay? Or you could reword it and say 85%, right, of the values or observations are less than or equal to whatever the given raw score is. So that's if you're at a percentile, right? Kind of inclusive in terms of like less than or equal to or worse than or equal to. If I say someone's within the 85th percentile, I'm not really specifying where they lie within the distribution. So 85% of the data, right, is kind of to the left of whatever that given raw score is, but they could be at the 50th, they could be at the 37th, right? So they're within a group. So that's a little bit less inclusive in terms of the equal sign, okay? But in order to calculate percentiles, right, usually we're going to be looking at a frequency distribution, and we have different examples So we have simple, which you guys looked at last week. We also have a grouped frequency distribution. And then there's another simple, but it's with discrete data instead of continuous data. So we'll keep going. But basically, the things you need to know is the raw score that you're evaluating, how many scores were in the entire set of data. So usually that's going to be your sample size. And in the more complex equations, we'll need to know a little bit more, but percentiles are percentages, right? If you remember basic algebra, a percentage is, well, they use words. It's is over of, right? How many do you have over how many did you collect in total? So we're gonna go through some examples, so this makes a little bit more sense. But you guys will have to use these equations on the exam. Since these are our first equations that we're going through, I'll kind of explain to you how they'll show up on the exam. So for our class, I would say the first exam and the second exam are the ones where you're going to have some hand calculations on the test. But when I'll give you an equation bank, so you don't have to remember everything. But on your equation bank, you don't have like this equals, right? This part wouldn't be there. So it would just say cumulative frequency divided by sample size, probably, times 100. And then you'd have to like figure out that, oh, that's representative of a percentile calculation for a simple frequency distribution. Okay, so let's do example. I feel like I'm talking a lot, which is my job, but anyways. So we have vertical jump data and the frequencies at which individuals met these particular measurements, okay? So if we wanted to figure out what percentile a vertical jump of 33 inches would be, we need to know two things. We need to know the cumulative frequency that occurs at this given raw score, and then we need to know how many people were collected total, right? Because those are the two components of the equation. So in order to create a cumulative frequency, we have to create another column in our table, okay? When you calculate cumulative frequencies, you always want to start at the worst score, okay? So I don't do it to purposefully trick you. Sometimes it's organizationally easier, but sometimes I would give you 26 at the top. I might give you 26 at the bottom, right? So you just have to determine for a vertical jump, the highest jump is considered the best jump. Well, what we aspire to do, right, is jump as high as we can. And then lower measurements would kind of be considered on the worst end of the distribution. Okay, so you start at the worst score that's in your distribution. I mean, at 26 inches is pretty good. So anyways, you take the frequency that exists at the worst score, and that is your cumulative frequency at that score. Okay. If we want to calculate the cumulative frequency for the next score in our frequency distribution, we take the existing cumulative frequency, add the next frequency, and then we get the cumulative frequency at this score. So basically what we're saying is that 6 people out of however many we've collected were able to jump 27 inches or lower, or they were able to jump at least 27 inches if you want to reframe it so it doesn't sound so dumb. Okay, so then we calculate cumulative frequency for a jump of 30, right? So we have 6 plus the frequency of the next group, and we would end up getting 12, right? And so we do this, add 7, cumulative frequency for people who jumped at least 33 inches would be 19. people who jumped at least 37 inches would have a cumulative frequency of 21, right? And so on and so forth till we get to the end of our distribution, okay? And the number at the end, so at the best score, whatever you deem that to be, should be equal to the sample size that you collected. So you can always check, right? But basically now we know, right, if someone had a vertical jump of 33, we would say 19 people out of 25, right, were able to accomplish that jump, or that was at least that jump, okay? And so their percentile would be 76, right? So that would be if we did 19 divided by 25 times 100, 76, right? So you report it as the 76th percentile as an answer. And your activities are also accepted if you present it as a percent or a percentage. Basically kind of means the same thing, okay? So if you have a calculator, see if you can calculate what the percentile would be if someone had a vertical jump of 38 inches.
Natalie?
Mm-hmm.
So if someone scored a 33, how would you say that in a sentence regarding percentile? Would you say like they're within the 76th percentile? Or...
Yeah, so if we're doing, when I worded these kind of openly so we could discuss this if it came up. Oh my God, I'm having issues. Okay. So if the person was if they had a score of 33, or their jump was 33, you would say they scored at the 76th percentile, right? But if you're including all of these people, then you would say, like someone who scored the 27, like they kind of lie within the 76th percentile, if that makes sense. But this 76th percentile is inclusive of all of these people.
Okay.
Yeah. We just have to be specific when we say like it includes like someone who jumped at 27 inches. So that's kind of the within concept. But if we're saying like this person is at a certain percentile, they have to have gotten the raw score of interest.
Cool.
Mm-hmm. Did anybody come up with an answer for this second one?
The 92nd percentile.
Yee.
2.
Right? So we have 23, right, is the cumulative frequency of people who were able to jump up to 38 inches, right? So 23 divided by 25 times 100. Does that make sense? We could do thumbs up, yay, nay.
I'm getting kind of confused of what, I guess what cumulative frequency means. Because in like the wording makes it sound like all those people in the 23 cumulative did 38 inches, or I mean jumped 38 inches, but I don't think that sounds right.
Right. So cumulative just means that we've compiled stuff. So like if your final is cumulative, it includes everything from the semester, right? Even though it's test 4, you're still being tested on stuff from exams 1 through 4. So you can kind of think of it the same way, is that whatever this score is, because everything is on a distribution, right? I can try to draw. This is also why I'm getting an iPad, because I suck at drawing with my mouse. But yeah, go ahead.
If you're going to incorporate then, going off that question, if you're going to try to incorporate like cumulative frequency into like the sentence, could you say like of the cumulative frequencies consisting of 19 people, they've 7 of them, or no, 19 of them finished within the 76th percentile?
Yes.
Gotcha.
Yeah. So it's 19 of 25.
Right. That's how you get the 76.
Yeah. Mm-hmm.
But the frequency is 19.
Yeah, cumulative frequency is 19. If you wanted to say who landed exactly at the 76th percentile, then that would be 7 people. But if you're saying who landed kind of within the 76th percentile, because I was going to draw. Oh my God, it doesn't look that bad.
Yeah,
Okay.
I understand. Yeah. The
Yeah.
within, because earlier it said like we said like, oh, at least 33 inches, and that just sounded wrong based off like all the people under that didn't score that high.
Got it. Yeah.
I understand like the concept.
Yeah, I could have worded that better. But if this is the mean, generally when you're looking at a cumulative frequency, it includes everybody to the left of that score. So, lovely picture, but yeah. Okay, so this is for a simple frequency distribution. If we're looking at a grouped frequency distribution where we have these lower and upper bound situations, we have a bit more of a complex situation. No, hold on. I don't want, I guess a laser pointer works. So we have this, which looks like a crap show. So X is going to be our raw score of interest. L represents the lower limit of an interval. So in Excel, we will build, we're going to build intervals in various ways. But it's the formula that you build in your like calculation area that is important. So I think in this one, I have it so that the end of the vertical jump is at 0.9, right? Or the upper bound of each interval ends at 0.9. And then the next interval begins at 15. But this isn't always an ideal way to set stuff up, because sometimes, like, what if somebody jumped a vertical, or they had a jump height of 14.95? Like, where did they go? So sometimes in Excel, if we have a lot of continuous data that's like multiple decimals, I'll tell you guys do the intervals at whole numbers, and then you just have to make sure you don't include. So if this was 10 to 15, you just have to make sure you don't include 15 in both of your calculations, because then you'd be counting people multiple times. But for this example, this is how we have stuff set up. So the lower bound is the low end of each interval. Upper bound is the upper end of each interval, right? So low to high. So L just represents the lower limit of the interval at which X resides within. So if we had a value 23, that would be 23 would actually be X, right? The lower limit of the bound that X lies within is 20. So that's kind of how we apply that. I is the size of the interval, and we calculate this by taking two adjacent groups. So usually I start either at kind of the low end or the high end, but I don't usually go in the middle. It shouldn't matter, but just for ease of calculations, usually I do that, because I usually build my equations starting from the top down. But you take two adjacent cells, or two adjacent intervals, and then you subtract either the lower bound numbers, or you can subtract the upper bound numbers. Okay, but they have to be low and low or high and high. It can't be like, I'm going to subtract these two. Woo! It doesn't work that way. So in this case, the interval size, we could say 15 minus 10, interval size is 5, right? You could look somewhere else and say, oh, 39.9 minus an adjacent upper bound 34.9 is also 5, right? So that's why I'm saying it doesn't really matter if you use lower bounds or upper bounds, but they just have to be adjacent interval sections, okay? So in this equation, if we were still using the number 23, right? I is a constant, it's 5. F is going to represent the frequency at the interval with which X resides. So again, 23 is in this grouping. So the frequency that we would put over here is 20. Okay. C is going to be the cumulative frequency of the interval smaller than the interval in question. And so we will get into that. But basically, again, you kind of say, who is, the elite jumpers, or what's the worst, worst score within the distribution. And that's kind of your evaluation, like, okay, well, we have to take a step backwards. If we had, this interval up here, we would go to the next worse than category. So you have to make sure you pay attention to orientation of tables. And we'll do several examples of this. But cumulative frequency is the worse than. So in this case, we would take the cumulative frequency that resides in this box if we're keeping X is 23. Okay.
Cumulative frequency is always going to be like the worst, right?
Yeah,
So,
towards the worst end. So if you have like the distribution, you fill into the left of your raw score, which is going towards the 0th percentile.
Gotcha.
Yeah. And then N is your sample size, which we should get in this case in this cell here, because we should have collected everybody by the time we get to the highest score. Okay. So similar to last time, you guys can help me fill this in, right? We start again at the worst end of our value. So this time our worst values are at the top of the table. So cumulative frequency should be,
Is it 5?
5, right? And then we would add 12, and we should get
17,
17, add 20,
37.
7, add 25. People are like, crap, math. And this is the nice thing, is that Excel, you make your equation one time, and then you just double click copy, and everything is done for you. Once you learn Excel, you're like, they should make a course on how to work this thing. That's basically what we do in this class. We cover quite a bit. Like if you went on LinkedIn, you could probably pass the proficiency test when you're done with this class, if you want to have like a mark on your LinkedIn, like I'm Excel proficient. Anyways, we learn a lot, but it's a very, very good tool to use. Okay, so side note, but we calculated cumulative frequencies. Okay, and now we have pretty much everything we need to fill this in. Okay, so I'm gonna skip over to what our questions are. And we want to calculate what the percentile for a vertical jump of 30 would be. Okay, so first we have to identify where does 30 land within our intervals, and we can see it's in this guy right here. Okay, so at this point I'm going to stop sharing, and I don't know if that worked. I'm just gonna do gallery and then zoom in on my face. Okay, so in our example, we've got a percentile that we're trying to calculate for. Okay, and the first thing, when you're in Excel, I'll show you this in the activity, but you put 4 parentheses because order of operations is really, really important when you're calculating percentiles for grouped frequencies, right? Because, oh no, you can't see my screen, but we have, I'll write it in terms of Excel down here. You've got the X minus L part, in the first parentheses, then, because you have to do that first, then you divide by I, so that's the next set of parentheses, and then you multiply by F, which should go in order, and then addition follows, and then you have to enclose the numerator over the denominator, close that, and then multiply by 100. Okay, so Excel, because you're writing it out as like one stretch, it's a little bit more complicated, but it should work. Anyways, if we're calculating this, I'll do it up here. What is X?
30.
30, right? Because that's what we said in our example. So we have 30 minus, what is the lower bound?
30.
30, right? Because it's between or included 30 to 39 or 34.9, right? So that's kind of this first part here. And then we divide it by I. And what is I?
I is 5.
I is 5, right? And I'm going to extend these down. So I is 5, okay? So we've got this part locked down. What's the frequency at that particular interval?
5.
15. 15, there we go. Okay, 15. And then what's the cumulative frequency of the group that's worse than where 30 is located? Oh.
62.
62.
62, right? So we say if you keep your sites in a row, right? Remember we said that worst scores are at the top of this table, the best scores are at the bottom, right? And you want to take the cumulative frequency of the group worse than the score you're evaluating, right? So cumulative frequency in our case would be 62, and then we divide everything by
90.
90, right? Our sample size, which should reside in the cumulative frequency box in the last cell. Okay. You guys can all read that whiteboard, right?
Yeah.
Okay, cool.
Natalie, if it was like 30.5, would you say the cumulative frequency is 77 at that point? Or would you still say 62?
If it was, 35 point, what?
No, it was just 30.5. Like if it was just a
Oh.
little higher, would you say it was 77?
No, so it's whatever goes in the group, right? So we could have done 30, 34, 35, or 33, right? Anything that lands within the grouping. I'm like pointing to my screen. I'm like, yeah, it totally makes sense, but you guys can't see it. Right? So anything that lands within this particular grouping is now assumed to reside at the same percentile.
Gotcha. So
Since
then it's
we're
always in
grouping them.
that group.
Mm-hmm.
Gotcha.
Yeah. So anything that's the only time we would use 77 as a cumulative frequency is if we were evaluating an X that was in this group.
Right. Okay.
Yeah. So that was fun. So if you calculated it out, it should be the 68.9th percentile. This is why I let you guys put percentages, because it gets awkward. But usually on your activities, I'll say, specify decimals or whatever. Okay. So let's do one more. If we were calculating the percentile for a vertical jump of 22, right? I won't write it so that you guys can kind of follow along in here, but if you want to write it on a piece of paper, feel free. Right? So what would X be in our equation? 22. 22, because that's the x we specified in the question. Right? What would L be?
20.
20, right? Because 22 resides in this interval. 20 is the lower bound. What's our interval size?
5.
5, right? So that would be I. What's the frequency?
20.
20, because that's the frequency that matches the interval within which x resides. It's a lot of words. English is hard. And then what's the cumulative frequency we would use?
17.
17, right? Because 22 is in here. So we do the cumulative frequency of the group worse than, where our x is located. And then we would divide by 90, because that's our sample size. And if you put that all together, you should get 27.8. So, yes.
If our vertical jump was like 11, what would our cumulative frequency be? Would it be a 0 or 5?
Oh, good question. So you still operate on the cumulative frequency worse than a given score. So in this case, you have an imaginary 0 here, right? Because when you're at the 0th percentile, you basically start with nobody. And then you add the frequency of the next group, right? And we get 5. So if we were calculating someone in this group, we would just use 0 in place of like one of these numbers in another situation. Cuckoo, cuckoo.
Could you round those numbers up, like to 69th or 28th?
Yeah,
Okay, thanks.
absolutely.
What was used for the sample size and
90. Yeah. So whatever the high end or like the best end of your distribution is, that's where your sample size should be located.
And then did you
if we
just
had
round
this-
up?
oh.
Oh, sorry.
It's okay.
If we were given something like this on the test, and it was like, let's say like 10, 15, 15, 20, like we would just assume the upper bound we wouldn't include in like the prior interval, right?
Right. And we do an example of that in the activity. So last week you guys used wait, I don't remember. Did I make you use a count ifs function?
yeah.
Okay. So that's what you would do for this one, right? Because you have criteria. It's kind of the same thing. So if this was 15, you would say, I want to count my data. If we didn't have these frequencies already, you say, I want to count my data within a given range if it meets the lower bound criteria. So if it's, in this case, greater than or equal to 10. And then if this was 15, we would just say less than 15.
Got it.
Right. But since this example, we're saying 14.9. So if we were sticking that in and we're ignoring the, someone who's at 14.91, for example, and we're just interested in these values, we would have to include those in there. But, I mean.
Wait, so if it was 14.91, we'd include it in the first interval then? Or the first grouping?
Yeah, but that's the problem with how this is set up, right? Because
Okay.
if someone, and it depends on the units of measurement that you have. If you have something that's more discrete, where you're measuring, by tenths, then this might be okay because the next highest score to 14.9 would be 15. But if you have something that's more continuous where you're, going past one decimal place, this is not the greatest way to do things. That makes sense.
Yeah, it does.
Okay, cool. So I've included some practice problems for you guys. We might come back to these if we have time at the end, because the chapter 4 part, honestly goes by pretty quickly, but I also have a video of me doing these ones in Excel if you want to know how to do them in Excel. So yeah, kind of skip over this slide for now and we'll come back to it at the end. I need to shift here. So before we go on to central tendency, does anybody have any questions on percentiles overall? We're doing okay. Yeah, I'm gonna take that as we're good. All right, so measures of central tendency are what they sound like. They are measures that land in the center of a distribution. So you have, I know for a fact, everyone has seen these words before. Okay. Mean, median, and mode. It comes back to this. So like I said before, in an ideal bell curve where we've got a perfect 50% on one end of the mean and 50% on the other end of the mean, all of these central tendencies or measures of central tendencies would be equal to each other. Okay. As it is, most of the time, nobody has a perfectly normal distribution, so that's not going to be the case. And there are certain things that we can do to figure out how to fix that. Because we'll talk about this next week, you have to have a normal distribution in order to run your statistics. That is that, and having random sampling are like the two key things that have to exist in order to run any statistics at all. Okay. Not calculations, but statistics. So if you're inferring information on a population, you have to have a normal distribution because the population is always normally distributed, right? But we being scientists can never measure the entire population. So usually we're like, well, let's get a subset of that population and hope that we included enough people that represent the diversity of the population, right? So there's certain individuals, let's say, who maybe are at one end of the distribution that should not be there, or they don't match who you've collected. Sometimes these two calculations would be great if you had an outlier, okay? So we'll go through these one by one. These definitions are going to be on the next slides. So let's get to it. So we're going to start with the mode. I think MO, it's the most common number, right? Or the value that occurs the most. And this is purely based on frequency distributions, right? So all of the tables that we just made, you can make those into a bar graph, which is, or a histogram also works if you have bins of intervals. But, right, you see, these are all the data points that I have, or groups if you're doing group frequency distribution. And you look at like, okay, well, how many people do I have in each of those groups or at each of my values? Whichever value on that x-axis occurs the most, that is the mode of your distribution, or of the mode of your data, okay? There are some times where you might have bi or multimodal variables, in which case a bimodal distribution would look something like a camel, okay? So two modes because there's two values that potentially occur at the same frequency. Multimodal, you would just start making a bunch of waves, okay? But that is known to happen. It's not uncommon. Pros to using a mode is it's very easy to determine, right? When I give you guys a bunch of data, basically you need to know what the minimum of that range is, what the max is, and then figure out if you want to do a simple or a group distribution, and then do your calculations, and it's done pretty quickly, right? You just find the biggest number, see what value that's attached to in your, measurement data, and then you're good to go, right? So it's super, super easy. It's a very quick estimate of the center of the group, but it's not law, right? So I like to point this out because if I erase that line really quick, and this is why I bought an iPad. Okay, it's an estimate, right? So you could have something that looks like this, where you're like, yeah, this is the center of my group, which generally it should be right, okay? But in terms visually, it doesn't really look great. But it could be that, 99% of your data falls in this range, and you have one person who lives out here, right? And then they essentially skew the data, which we'll talk about in later weeks. Might be next week, actually. But the mode should always give you an estimate, regardless if there's an outlier out here or not, right? But it's an estimate, okay? Because there could be some situations where maybe you have high frequencies in the center, where your curve is a little bit more flat like that, in which case, there's not very many outliers, but you could have the mode in the center. It might be shifted or something like that. But that's something to note, is it's an estimate. I did a horrible job at circling that word. Okay. But generally, it's a fair description of central tendency when the data are normally distributed, which is our lovely bell curve, right? Cons of using a mode is that it is a terminal statistic, okay? Think terminal, usually if you terminate something, you end it. So once you calculate the mode, that is all it's good for, is to tell you this is the most frequent value that, showed up in the data set. It doesn't, you can't put it into a t-test or an ANOVA. It's done, okay? So it can't be used for further calculations, which isn't super helpful for us, at least in the terms of this class. And it also disregards extreme scores in the example that I showed here, okay? So, any questions on the mode? Cool stuff. Okay, so the median is the middle number. It is in the middle of the distribution. Thus, we would expect it to live at the 50th percentile. Okay, and it's important to remember that the median is rank ordered. So you list values from small to large, and then you pick the middle number out, right? In Excel, there is actually a median calculation, so it's pretty easy to calculate for this class. Where we get into issues sometimes is I'll give you a frequency distribution table, and then you'll have to build your ordered list. But I think I have an example at the end of the lecture. We can do that if you guys want to. But if n, or the sample size, is odd, you take the middle score exactly. If the sample size is even, you take the average of the two middle scores. Okay, and Excel knows to do this, so that's why I said it's a wonderful tool. Pros to using the median: it's very appropriate for ordinal data, right? Because you get the exact middle of the distribution. It's also good for highly skewed data. So this picture where you have this tail over here, regardless of if you only have one data point or you have, maybe a couple, okay, you're still going to see all of the data listed out from small to big, and you still get the center, right? So the median should typically, if you have skewed data, it should still live somewhat close to where the center of the distribution is, similar to the mode, okay? But it's just not as affected by extreme scores in its calculation because we're only looking at the center 1 or center 2 values of our data, okay? However, cons is it does disregard extreme scores, and then I lose people because it's both a pro and a con for when we have skewed data. But the problem is it does these outliers aren't going to affect the actual calculation of the median. So you still get an idea of where the center is. However, you don't know that these actually exist if you're only looking at the median. So it's both a good thing and a bad thing to use the median. It's also a terminal statistic, so once we calculate it, we can't really use it for anything else statistic related. Okay. Any questions on the median? Okay, I'm gonna take that as a no. All right, so the mean, which is probably the most commonly used measure of central tendency in statistics, is the average, right? So we take the sum of all the scores and then divide by the sample size, okay, or how many scores we collected. And the nice thing about the mean is it considers both the frequency and the quantity of scores. So when we look at the mode, we look at what's the highest frequency, right? If a number keeps showing up, and if we had like a rank order of data, the number keeps showing up, our mean is going to centralize towards that value, okay? In terms of quantity, that kind of pulls from the median aspect where we're like, well, how many numbers do we have? Where is the center if we counted how many values we've collected altogether? Okay, so it kind of takes into consideration both of those two things. However, it's also the most sensitive measurement, which is both good and bad. So when we look at our list of pros and cons, the pros is that it is sensitive to outliers. So if we had a distribution that was skewed, right? I keep drawing the tail to the right, but the tail could be at the left as well, right? If we have skewed data, generally we would expect our mean to exist in the center or at the peak, right? If we think of a perfectly normal distribution, the mean should be right in the middle, okay? What happens when you have outliers is when you're summing up all of these values and you have this extreme value over here, the mean gets dragged towards that tail, right? So in that sense, we're able, if we do normality testing in addition to calculating the mean, we can figure out if an outlier might exist because we have the sensitivity built into the equation, okay? Which means it considers all aspects of data, right, including the outliers that we might not want. It's not a terminal statistic, so we can use it to do more statistical tests, such as, let's say we wanted to compare 3 different groups of people. Let's say they're majors at Long Beach in the kin department, right? So we have our exercise science people, our athletic trainers, and our fitness, right? And we want to see, you know, how the groups are different based on their grades or GPA, right? So we would take the average GPA for each group, and then we would say, based on our samples and their averages, are they significantly different from each other or not? So the mean is the one that's a central tendency calculation we'll be working with for the rest of the semester pretty much, with the exception of activities that ask you to calculate the mean, the median and mode, but past exam 1, we don't really look at the other 2. And this is also the most appropriate for ratio and interval data. Again, kind of looking at the spectrum at which values lie within. So remember, ratio data, a value of 0 or absolute 0 represents the absence of a score. interval data, absolute zeros don't exist, so they're kind of part of the range of measurements that you could collect from somebody. But it's the best, this is the best calculation to use for these two types. Nominal data, not really. I actually have used it on nominal data just to see, like, on average, which category was the most prevalent within a list of categories that I was sorting people into. But generally, we don't use the mean for nominal or ordinal data, just because of the types of data that they are and how numbers are represented, right? Because ordinal data, remember, we don't have a discrimination between adjacent scores within the ranking. For nominal data, usually if we use numbers to represent categories, they are referred to as string. Yeah, they're referred to as string data in terms of, like, they don't actually represent a value. So 1 doesn't mean 1, it just means this is category 1, right? So calculating a mean doesn't really make sense for ordinal and nominal. So we don't use it for those two usually. Cons of this is that it is affected by outliers, right? So good thing is that it's sensitive because it can detect outliers based on fluctuations in the actual value. But the bad thing is if you don't check for normality and you're not able to pick up that you have outliers, then we can't use the mean to compare a sample to a population, because that's the big ticket. And we go into this more next week, but your sample has to be as similar as possible to your population in order to draw inferences about your population. So that makes sense. So, any questions on the mean? Okay, so our last slide, is looking at a frequency distribution, and then I also have a graph. So if we graphed all of this out, it would, in a line, it would look like this, okay? Clearly, we do not have a normal distribution because this person is out here, right? So if we X to this person, we're like, die, and we don't include them in the research, then I would say this is kind of okay, right? But what I wanted to do really quick, what's the best way to do this?
So Natalie, due to that outlier, that you're saying the mean would be more affected than the median?
Correct.
Gotcha.
I don't want to keep my ink annotations. So hold on a second. I'm gonna stop sharing and then I'm gonna reshare. Sharing is caring. Okay, anyways. So this is, no! Okay. PowerPoint is going wild. All right, we're gonna reformat here. And if you have Excel, you can pull it up really quick and do this with me if you want to. And all we're gonna do is copy the table and paste it in here. And then I can zoom in for you guys so it's not so small. Okay, so in order to do calculations, we can't have this table. So there's two ways usually that I'll give you guys information on an exam. Either you'll get like a big data set, like I've given you before, if maybe you were generating the frequency distribution, in which case that's pretty easy because you just highlight whatever the data cells are, and you say, I want to calculate the average of this range. When I give you a frequency distribution or a figure, usually if I give you a figure for these types of questions, it'll be a bar graph. But if I give you either one of these two things, you have to build your rank order. So if we were, I'm just going to call this data, right? We say the value of 1 shows up 2 times. So I would put 1, 1. And then the value of 2 shows up 5 times. 2, 2, 2, 2, 2, right? Value of 3 shows up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times. Kind of see where I'm going with this? 4 shows up 9 times. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. Wait, my Zoom thing is in the way. I need to move it. I made one too many. Okay. And then 5 shows up 8 times. I'm just gonna go like that. I need 2 more. Okay. And then 6 shows up 6 times. Right? And then you just build this ranking system. 7 shows up 5 times. 4, 5, 1 more. 8 shows up 3 times, and I really apologize if you get motion sick when you look at a screen moving. That's torturous. 9 shows up 2 times. 9, 9, 10, and then we have this 25 doodad out here, right? So we have our ranked data, and then we can perform our calculations. So we're doing the mode, which we could easily get by looking at the frequency distribution, right? So what would the mode be?
3.
3, right? It's the number that, or the value that shows up the most times, because frequency is 11. The median, actually we calculate by saying equals median. I cannot spell. Still can't spell. Damn, that sucks. Okay, so we do median, and then we say, I want this range of data to be calculated, right? In this case, we get a median of 4. You could also say, how many data points are in this entire list? And we see a number 53. So 53 divided by 2, and then that gives us the middle, pretty much, right? And then we just count inwards and then find it, but that's really annoying. So that's why I use that function, right? And then we can do the average, or I'll type mean. And I'm gonna do mean with the outlier so that you guys can see how the mean is affected. So in this case, we're gonna do the average of this data set, right? And this is the average that we get, 5.0 something, right? If we calculate the mean, I just realized this is kind of confusing. With the outlier, this one will be, I'm just gonna say no outlier. You guys are like, it's without, ah. Anyways, if we calculated it without that value of 25 at the end, I'm gonna do, no! That was rude. All right, I'll just do it the hard way. We'll go here. Okay, you can see the average is actually 4.69, right? Which in terms of quantities, it doesn't seem like a whole lot, but the mean should be closer to this end of our graph, right? So let's say, la 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 la. Gosh, get out of the way. I can't see anything. I hate this. Zoom. And now my computer hates me. Okay. So insert, let's say, I'm going to do a bar graph instead. I now see why I did a line. That would make more sense. Now, if I do a frequency, that would be better. Just kidding. I'm gonna do a histogram. I'm just talking to myself at this point, so anyways. This is what the data look like with the 25. And remember, usually when we have a frequency, we have to orient these so the x-axes match our value. So just imagine that 11 is actually 25, right? But if we did a graph without 25, oh wait, in which case we would just do these guys. I don't know why. Why am I this way? Okay. Go here. You can see the shape is a little bit different. Right, so if we line them up and we added 11, you can see that this peak in this graph actually shifts to the right. So if I added an extra value on this side and expanded it so that each of these x-axes were the same number of values, you would be able to see that this shifts towards the tail. And so when we're doing research, ideally, we don't want tails. So when we have outliers and they drastically change the shape of our distribution, we cut those people out and then we report it. We have to report it. So we say, that's sometimes when you see research and it says like, oh, we collected 55 people, but we only ended up analyzing 33 because maybe 27 were oddballs, or 17. I don't know. Anyways, so if you have outliers, you usually want to kick them out, right? But you can see when we have the outlier in there, if we don't have the outlier, so if we're looking at these three numbers, they're generally lined up with each other, right? And I think that's what my last slide is. Okay, so if we had no 25 in our data set, our mean would be closer to 4, which is our median, right? But since we have 25, it pulls it out towards the outlier. So that's what I mean when I say that the mean is sensitive to extreme scores. But anyone have any questions on this? Or how I made this? Cool. Okay. Sometimes I forget because I've gotten really good at Excel since I've had to use it so much in grad school. So I'm like, and then it's all done. But any general questions on the lecture as a whole? We cool, fam. All right. So I'm gonna stop the recording.